Okay. So after the first assignment, now we are moving on to the second coding assignment that is based on model stealing. Before that, we would like to go around with some announcements. Unlike in the first assignment where you only submitted a report, a PDF, this time you are supposed to submit a zip file that contains a report as well as a very clean document, well documented code. Usually, you just download the zip of your GitHub repository such that it does not contain any big models or large artifacts. Make sure you add a.
You want select formatting?
No, it's fine.
Are you sure?
Yeah.
Okay.
It's fine.
Okay.
Make sure that you have a nice readme in your code so that we don't have to sit and open every code file and figure out what it's supposed to be written. Just mention which files does what and which can reproduce your best result. And other than that, the report format still remains the same. One addition that please make sure that you add your CMS team ID so that it's better for us to figure out who of your like the two teammates are and we can assign your grades properly. It's other than the report format remains the same. And yeah, that's it. The deadline is 26th May 20 EOD end of the day, and no exceptions for email submission via email.
So please submit time to time to the and then post for after the deadline, okay?
Since the next 27.
It's updated 26/5/2359. I think it's already updated if you can see.
So what is the
Since I can see that the
It's updated, I think so.
no, yeah, in assignments,
Yeah.
In the main page, not here.
Yeah, but you can always check via the
Yes,
submission
here
that it's updated.
pages.
Yeah. And these are the announcements. Please make sure to submit a zip, not just the report. You should make sure you have both the things in the zip file. Moving towards model stealing, already we have a small recap of the idea of model stealing, that there is a victim model that's about to be stolen. There's an adversary who's if the victim model is on a black box access, and it's going to be queried via API. The adversary does not have any other idea about what the model was trained on or what are any other access to the model other than just getting the final low dimensional outputs, usually labels. If he or she has the idea of what the training data was or what the model is actually based on, then the data would probably be in domain data, otherwise out of domain data. And if it is a white box model, then yeah, the adversary will have access to all the training procedures, training data usually, as well as the outputs would now be logics, not just labels and whatever the adversary wants. And that is how the model would be stolen. Even the metadata from most of the models usually contain what type of data it was trained on or what is the architecture of the model. That way the adversary can actually steal the model architecture as well. And that's your task. Your task is you are the victim here. Your model is being stolen. And there are around 360 suspect models that you are supposed to figure out whether they were stolen or not. You know, as the victim, you know that which of the training indices, which of the training data was used in the model training, your target model, victim model training. You don't exactly know the exact training procedures or the history of the data, but you have idea about the training hyperparameters and all that. You don't know the provenance labels of the suspect models. Basically, you don't know whether they were stolen or not. And as a victim, you have to figure out whether these models were stolen or not stolen. What you submit is you assign a continuous stealing confidence score from 0 to 1. Higher the confidence score, more likely that the model was stolen. And usually a model is considered stolen if it's directly copied or derived from the target model. And even some transformations were applied substantially. more detailed on which of the models would be considered stolen and not stolen will be in the future slides. And as similar to the assignment one, it's 30% of the models for the public leaderboard. For the private is the remaining 70% of the model. Make sure to not overfit to the public scores because this time there are 360 models, not 14K samples. So there is a higher chance that you may overfit a little to the 30% of the models. What counts as stolen and not stolen? It's easier to figure out what is not stolen. Basically, if it was trained from scratch, you are just picking a random, just having a ResNet model and training it from scratch with different data or a different training history, different training procedure, it's considered not stolen. And even if a model is using a very similar data to as the victim model, or even the same data distribution or some overlap between the two data set of your model and the new model, it would not be considered stolen. What would be considered stolen is just directly picking up the target model and using it, applying some transformation to the model before stealing it or after stealing it, basically pruning, channel shuffling something. If you are just using taking the directly victim model checkpoint, final checkpoint, and fine-tuning it further, training it further, it will be considered stolen as it is derived from the target model, as well as the student model trained on target's output, even with out-of-domain data, basically a distillation model where you have the target model, you are just querying it with in-domain data or out-of-domain data, getting the labels, and just training a new ResNet model with that input-output pair. That will also be considered stolen as the target model is involved there. And yeah, a directly copied or derived model. What are the target model, the victim model details? So it is a ResNet 18 models, 100 classes, which is trained on CIFAR 100 dataset. And you can get it's trained on a subset of CIFAR 100 dataset, but you have the information that which subsets were used, what training data was used in this particular file called main idx.json. It just contains a lot of indices of the training data from the CIFAR 100 dataset. Some augmentations were applied to the images and to the training data before actually training this model. They were random horizontal flipping, basically mirroring the images, mirroring the images, biased random cropping with reflection padding of 4 pixels. So basically a 32 cross 32 CIFAR image is now 36 cross 36, and the bias, basically with this bias, it means that you are not always, the model was not trained on the full data set, but just randomly cropped with a upper left portion of the data set, as well as normalization, mean and standard. This was also there for the previous previous task, similar that normalization was applied to the particular images, and if you don't apply this normalization to your images while querying the model will not understand that it's the same images that it has seen. So it would be like a silent bug, would not give you meaningful answers even if your model or your training data is correct. So make sure to apply this transformation. It is also already present in the task template.py, which I'll show you. So just like that, make sure you always have this. How was the model trained? The model was trained with cross entropy loss, no label smoothing, SGD with a momentum of 0.9, weight decay for regularization, batch size 256, and initial learning with 0.1 and cosine annealing schedule. Basically, it started with a learning rate of 0.1 and then decreasing gradually using the cosine, decreasing gradually smoothly as following the cosine curve, not just decreasing in steps like 0.1 to 0.005, but rather continuously. The evaluation metric is similar to last time, that is TPR at 5% FPR. You are going to assign a confidence score. True positive rate is fraction of actually stolen model that you correctly identify when rank highly. false positive rate is fraction of non-stolen models that you are actually counting as stolen. Basically, the false alarm which we are trying to reduce. So your threshold is 5%, 0.05, where you are making sure that at this particular threshold, how many models can you correctly identify as stolen. So yeah, the same graph, 0.05, you want to make sure that how nicely you can get a high true positive rate. How do I remove this?
So, cooking more? No,
Okay. Never mind.
it's one that's hiding floating controls.
Oh, thank you. So basically, at the small threshold, you want a high true positive rate. Now we move towards the code. Unlike last time where we had one single file having both the things together, which caused some confusion for some of the people because they did not know some submission issue. So this time we have divided it into two files, which makes it a little easier for you. We'll go through those slides, those files as well. So this is the task repo that you have access to. You can find the link in the task description that is already provided. And going a little bit through these. So this particular directory has all the 360 models that you are supposed to score. And that is the target model where you have the weights and the indices, just a very huge list, a JSON file with a list. Going back to the task template, as usual, the imports, loading the model. Can you guys see it? Yeah. So it's a resonating model. The architecture has been changed a little to adjust the CFAR 100. And this function is going to basically load the model. This is the checkpoint path that you are going to give, basically the .safe tensors file that is in the target model directory. Or this is the same way how you will also load the suspect models. You can use it either ways. It will be loaded into the CPU. You can change it to CUDA devices if you are using the cluster. This will load the model, load the state dictionary, and in the eval mode, make sure you are using it in the eval mode so that you don't, since PyTorch uses the whole gradient statistics every single time for the inference as well, just make sure you are loading it in eval, it will make your code run faster. The transforms have been applied here. So every time it will load the image, the transforms will be applied. You can download the whole CFAR 100 dataset and just give the path here so that for the inference, it's going to load the model. It will get the first image. X will be the image, Y would be the label here. And this is the inference part where you are just giving the model the input of the first image. And it will give you the logits. Since you have white box access, instead of labels, you get the whole logits. You can just have a nice softmax on this to get the logits, to get the label. This will just print the true label. The logit shape here would be 1 to 100, considering it's CFAR 100, so 100 classes. And yeah, that will just print the logits. What would be the submission format for this on the leaderboard? So what you want to do is you are going to submit a .csv file where one of the column is the ID. The ID is the model number starting from 0 to 359, all the 360 models, and simultaneously the score for each of the models, the confidence score. In float, make sure it's not 0 to 1, it's a confidence score. And this will generate a nice random submission for you to try it out for the first time without having applying any particular attack. I already see that some of you have started submitting and solving the assignment. So make sure later on you remove this or comment it out so that it accidentally doesn't overwrite your submissions. Going back to the submission, this time the submission.py is a different file. And yeah, just loading. It's like now general instructions similar to what you had for the first task. Just make sure you are not having any duplicates, no missing entries in the CSV file, and make sure it's the score, not like the probability value, the confidence score, and not just raw numbers or any strings like stolen or not stolen. Avoid extra columns. Some people last time I think had these issues in the submission that their submission file had an extra row which created issues. So, and yeah, I think that's it for this. For here, this is the base URL. Do not change this API key. Here you can add your team API key. The team API key is only the 16-digit hex code, not the initial team underscore whatever the team name. That is just for you to understand that what is your team on the leaderboard. You are already familiar with this. Do not change this or your submission won't reach us. And the file path, whatever submission.csv you generate, you can just put it here. And other than that, you don't have to change anything here. This is just a small, all the changes you are supposed to make is here and here. And your submission is ready. Any issues with the coding part? Or what to submit, what to not? Okay. So then we can move forward a little, giving you a little idea on what you can try. So you have already learned in the lecture, the video slides, knockoff nets. Basically, you are, as an adversary, you only have an access to a model in a black block, a model which is black box. You only have a query access to that. You are going to query the model with the images and it will just give you the output label. How would a knockoff classifier work is that it will now train another model, a similar architecture model with these images, and the output basically it will label your input samples. Now you have an input output pair on which you can train a similar architecture model. It does not exactly fit in this particular task assignment description, considering you have white box access to the models, but the main idea here was to just give you that this model mimics the actual victim model out, like the way the actual suspect models would have, the suspect models are going to mimic the behavior of the target model. So that is something to look out for if the models are trained in such way that it's on a similar output or in-domain data. And second would be a weight-derived stealing. Basically, there are possibilities that the attacker who has stolen your models have just directly used the identical weights or just applied some transformations, and now the weights look a little different, but the function is the same that the actual model was supposed to do, and maybe just started fine-tuning from your checkpoint. So your weights are initialized and just trained, so changed lesser as compared to like if you would start with training a new model. So knockoff is going to leave some, like if it's trained like a knockoff type, it's going to leave some traces in the behavioral part of the model, while if it's just this weight derived stealing, so then it's going to leave traces in the weights. So for a good detector, what you want is to make sure that you are looking into both of these concepts. So you do not leave out some of the models, or you don't get some of the score assigned, like the models assigned wrong answers. So it would be good if you can look into both of these. And probably if your detector is able to figure out how to detect both of these cases, I think the task is quite solved. So a hint. Any questions?
You mentioned that one way of actually stealing is that copying the exact weights, but do the attacker have access to exact weights? Is it white box for attacker?
So not in knockoff nets, here it's black box, but we are giving you a white box access. There are possibilities that some models are just given the full, like they are just published on internet, and then someone starts training from your particular checkpoint, but does not give you some credit regarding that they have used your checkpoint.
That's right, but generally the model is published on the internet. Actually, the others they can use it generally. So
Yeah, it's allowed.
It's
It's
cannot be
allowed to be.
considered that
Yeah,
this
it's
is a-
allowed. It's allowed, but just a case where it's easier for you that way.
Right.
There are a few cases, for example, from Meta, that they released Llama models that you have non-commercial use license. So basically, someone uses this model at Llama 3.28 billion for some commercial use, and it's actually violating the service. So then, even though model is open source, the weights are open, they're not supposed to use it for commercial cases.
A lot of repos are also gated repos, so they need to know who is using your model. On Hugging Faces, you can see that. So,
We know the weights of the suspect models.
yeah, you have full access to the suspect models, so you can.
On Hugging Face, we have all the weights released.
It's all here. All the 360 models. Just make sure it starts from 0 and not 1, so 0 to 359. And yeah, so you have all the models. It loads the same way as the target model, so you just need to change the checkpoint here. Just need to change the checkpoint here to load a target model or a suspect model. Any other questions regarding the assignment? Okay.
I think here the main part is really to think about how the model will be stolen in this case. So is this part of course is just to copy the model, right? But also then you might also think that one can, for example, fine-tune the model, as we mentioned here, also prune the model, or even distill the model, right? So for example, there are many cases that you want to have from a smaller model, small model to a bigger model. But also situation is also one way how to, in this case, tune the model. So basically your task is to give a score what extent the given model might have been derived from the liquid model.
All the links are in the PDF. You can just find everything here. They are individually linked as well. If in case there is another issue, the bias and augmentation are also mentioned here. And the detailed idea on what you are supposed to submit exactly for the whole report. And the code repository is also provided in the task description. And some references for you to start on. Knockoff nets is the example I gave. And the second weight difference example is something similar to what model diff does. And I think, yeah, that's it. Yeah. So if you stand